Okay, thank you, Ming. It's great to be able to be here and give the presentation and at least to see all the familiar faces and see friends and colleagues. It's been a long time not being able to see everyone. So what I'm going to talk about today is the coupled interactions in superconductors and mostly the ion superconductors. Heiko Performer has given a talk recently in this series already, talk about the pneumaticity and tuned by strain gauge. So I'm going to talk about different subjects. I will try to say two things. One is the coupled interactions in ion selenide. The other will be how to engineer interface superconductivity in ion selenide STO and with LTO, STO interface in combination. I will go through when the work comes up, I'll acknowledge the collaborators. For the time domain experiment, really it was Simon Gerber, Shurong Yang, Patrick Kurtzman, Wei Shen Li. Our thin film work really started with the three, James Lee, Felix Schmidt, and a lot more. And some of the recent work really, so you contributed a lot. And now I'll touch one or two slides of the cuprates. That's a long-standing collaboration. And a lot of work here benefits from the interaction with Dang Hai Li and Tom Devlin. Okay. So let me, for the first topic, let me start out with ion selenide. That's the pressure dependence. That's the work of Jason Gu. And we know it's a low TC material. Under, I would say, modest pressure, the TC went up almost by a factor of 4 to 5. Okay. So this is very interesting. And when you look at more detail, it turns out that one of the most interesting things is, this ion selenium layers is the height of the selenium atom in this case, and the extremely sensitive way function of this height. And you can see either different compounds, they go this way, or same compound under pressure. And that's the pressure dependence here, the red point. Now, this reminds me about some of the work Mingyi did when she was doing a PhD. And you can see that there's a sort of reminiscence of this sort of shape of the dependence of superconducting transition temperature. That is the horizontal axis is the boundary normalization, the vertical axis is the superconducting transition temperature. For different orbitals, that's the X, Y, Y, X, Z, Y, Z, and this is the X, Y orbitals. They all show this sort of shape. One wonders whether there are some underlying linkage between this kind of shape of TC dependence of structure, also the electronic structure. So the question really raises, it appears that there's a linkage between correlation structural change and TC. And how one then question will be, what happens to the electrons if you move the atoms up and down? What happens to the electron-phonon interaction in the presence of strong correlation? Okay. So this has been a question I'm interested in for a long time in the cuprate context. So the challenge has always been how you will sort of go about measuring it. The traditional way of making electron-phonon measurements is subject to certain assumptions. For example, you can use Raman or optical and many other ways to measure it. You always need some sort of assumption, the Baire dispersion, density of space, something. So if people are not agreeing with your assumption, then they wouldn't agree with your conclusion. So the question will be, can we sort of devise a measurement that is a direct measurement, independent of this sort of assumption? So this leads me to the work we did using time-resolved experiment. In the time domain, you can possibly do some experiment that to achieve a precision which is not possible otherwise. So that would all go. So the idea is that I'm going to move this selenium height up and down through some sort of excitation. Okay. So if I can measure this height change directly, and I can also measure the band structure change directly, both are direct measurement. By doing that, I'll be able to make a direct comparison of this, which will relate to a microscopic quantity called the deformation potential. So if you can do that, then of course you can try to extract information on the coupling strengths. Then you can also use that to gain insight about iron selenium physics. Okay, so the technique we're using is the combination of time-resolved photometer. Here's a spectra. Instead of traditional photometer with one photon, now you have two photons, one pump and one probe. And in this case, in a conventional photometer, you only see states below the Fermi level. Now you can see that before your pump arrives, everything below the Fermi level. But when you now, if you do a pump probe experiment, you see states above the Fermi level because they were pumped up by the first photons. Then you can see the evolution of that. Okay, for example, how the direct surface state evolves in this particular example. Okay, so you can also actually use that to study driven system. But what we want to do here today is to use this technique to do a precision measurement of a ground state property. How are you going to go about doing that? In physics, at the end of the day, everything boils down to signal to noise. And we know a very powerful way to improve the signal to noise in physics is the locking technique. But traditionally, the locking is done at gigahertz type of frequency. So you can make a macroscopic measurement, but you cannot use that to make a microscopic measurement. So our goal was to push this locking technique into the terahertz regime and using the intrinsic frequency of the phonon in the system to generate a reference frequency, therefore to improve the signal to noise. So the idea will be try to use the IR pump and instead our incoherent excitation. If you're lucky, you actually can generate a coherent excitation. In this case, you of course can now generate a reference signal. Now you use X-ray to measure the lattice constant and use time-resolved photomaking to measure the band structure. Combining these two will give you the information of what you want, the deformation potential. So here's the plot showing the pump probe X-ray diffraction intensity. And you can see that aside from this sort of background, you see a beautiful oscillations of the vibration, in this case, the time domain in the time frequency. And if you do a Fourier transform, indeed, you see a mode, the A1G mode, and at a frequency of 5.33 terahertz. Okay, so this will allow you to learn something about. We're pretty lucky that Raman scattering is done in this case, and it turns out this mode is exactly the vibrations that are moving these atoms up and down. So that's what we want. Okay, so here is a time-resolved photomation experiment, and you can see here. I hope you see the vibration of the photomation spectra as a function of time. Okay, let me try to run it once more. I hope you can see the vibration of the photomation spectra. That's sort of 1.5 picosecond time scale. And if you now put these two together, the upper ones is the vibration of atoms up and down, And please look at the scale. It's a very, very small. It's from here to here, it's 0.8 picometer. It's far less than an angstrom. This constraint, as you will see later, we know that a typical material have a lattice constant at about a couple angstroms. So you better not change the lattice constant by 1% or more, because chances are if you change the lattice constant by more, you may well be studying different material, not the material you intend to study. So that constraint, and given the fact that this is less than 0.01 angstrom, and given the signal to noise, you can see this technique can give to you. That's the power of diffraction. Now you can see that simultaneously you see also the signal from the band structure, in particular the top XZ and YZ band show similar oscillation. Okay. So now if you put this together, then you can see that. Now, as I said earlier, we want to make a ground state measurement. That means you need to ensure that you are in a linear response regime. And this shows the fluence dependence of this amplitude of delta Z. You can see that as the fluence going towards zero, the amplitude also going to zero. So you are in a linear response regime, and same thing extrapolate the band structure. Now, if you take the slope of this one and the slope of this one, then you divide them, and you end up in a situation you can try to learn something about the deformation potential. Okay. So it turns out that the deformation potential in this system has been calculated. Both the density functional value is about 1.6, or the dynamic mean field theory, where the strong Coulomb correlation is more explicitly taken into account. This theory work is done before our experiment. And you can see that the experiment agrees with the dynamic mean field theory much better than the density functional theory. What the extrapolation, of course, is to say that in this context, you have to take into the correlation effects to get to the experimental result. Also, it says that the strong Coulomb interaction actually significantly also enhance the deformation potential. Therefore, also the electron phonon coupling. So it's to say that in those coupled systems, they have a lot of ways to influence each other, and that probably is really the underlying reason of the riches of physics in this system. Okay. Now, we are also in this context looking at what you look to try to benchmark this technique more, and you can see that the photoemission spectrum on the left-hand side, you see the time dependence of the photoemission spectrum. Those are picosecond time scale in unit, and if you take a cut, then you see all those oscillations. And if you do a Fourier transform, and you can see the two A1G phonon vibrations in this system. Again, it's convincing because you see all the phonons in the electron spectrum, okay, through the electrons. Those are all work in progress. Now let me come to the second subject, namely the interface engineering. Our work really have benefited a lot from the contributions of Donghui Liu, Makoto, Hashimoto, and Rob Moore. When Rob was still at Stanford, now he moved to Oak Ridge. And you can see that's the beam line, and that's the MPE system. It took a lot of effort to set it up. And so the example I'm going to talk about is the case of one unit cell on selenite. That's the same compound which I mentioned earlier. And by the way, the earlier experiment, femtosecond locking experiment was also done on thick iron selenium films. The bigger the films have a better, larger size for this sort of experiment. But now I'm going to talk about single layer, so it's a different subject. We were motivated by the work of Chip and Xue's group in Tsinghua University. And in their case, you can see that what they find is if you grow iron selenium one monolayer on top of strontium titanate, okay, what you find is that this system actually had seeing a gap is about 20 millivolts. So it sort of is a really much higher superconducting gap than one would have expected from the TC of this system. As I said earlier, the bulk form is about only 8 Kelvin. So that generates a lot of excitement. So we also looked into that. And we tipped at many other groups to find out that we can see the Fermi surface, which is a pocket near the Brown zone corner. Okay. But what I want to focus on here now is a different feature. Let's say if I make a cut across the Fermi level, I see a band structure, look like this. Look at panel C. Okay, you see a band sort of electron pocket in this way. But when you look carefully, you see a copy of this band here. You see a copy here. Okay. Now, if you do to enhance that, you can do a second derivative. You see the original band A, and you see its copy A prime. Here you can also say I see a band B, and it's copy B prime. And you will say, well, where is it? It's so noisy. When in doubt, go back to the original data. You can see, you may question whether there's another feature here. But when you go back to the raw data, I hope you'll be convinced that there's a feature here. That's the B prime. So there's a copy of this being shifted by almost 100 millivolts in frequency. And the copy is very loyal in the sense that you can see the subtle band back, that is the superconducting gap, okay? And the copy has the same thing. This work shows that this sort of phenomenon of replica copy happens only in one unit cell. If you go to 2 unit cell or 30 unit cell, this sort of replica phenomenon goes away. Okay. So the 1 unit cell has something special about it. Here you see the temperature dependence, and you can see that it's at 10 Kelvin, 30 Kelvin, 50 Kelvin, 70, 90, and 120. You don't see any change. Okay, this certainly is not related with the superconducting transition. 90 Kelvin is clearly above that. Okay, so what is it? And it was inspired by the idea of Damhai Li. We think this is a result of electron phonon coupling. So if I will make a cut and you can see the original band, then sort of replica band. And with the lover's eye, you may even see a feature here. Indeed, the more recent work by the Cornell group, Carl Shen, they have analyzed this feature and actually gained more insight. So that the lower part is the formation spectra of hydrogen atom. I should say that this sort of behavior as a second, peak, the main peak and a satellite peak, another peak. This sort of behavior is very rare in solid. In gas, you see it; it's extremely rare in solid. And the interpretation is this replica really is a coupling of the interface phonon with the Johnson tightening phonon. In this case, it's about almost 100 millivolts. So they suggest that there's strong interaction between the film and the substrate. This is the reason why this play a role enhance TC in this way. That's their original work. One of the key things I want to stress that this analysis really shows that it's a small Q forward scattered phonons, just like a capacitors in this sense. Okay. Now, Deng Hai and Tom Debro's group have done more analysis. They assume some sort of electronic pairing for the film itself, and with these additional channels, it can give 50% boost to superconductivity. Okay. The group has since refined the theoretical work, and I just want to reference that there's a blue shift of the mode, and also it appears to require smaller coupling tungsten to do the same thing. So experimentally, I just want to make one contact in this work with our recent work on the Q plates. In the Q plates, it's in the same way. We find that, I wouldn't go into the detail, there is a feature in the formation spectra, this sort of dip in the spectra, which is a coupling feature. And if you monitor this, as you go from high doping to low doping, you see your TC superconducting gap changes by a factor of 4 in a very narrow doping range. It turns out in the same doping range, the pseudo gap phenomenon changes a lot. Also, the electron phonon phenomenon changes a lot, all in a very narrow doping range. So the idea will be all those interactions sort of forming some form of flying wheel, one may say, and they enhance each other. So in that spirit, those coupled interactions probably doing something similar here. Now I want to go back one more thing to say that you can see a more refined experiment with study on different substrate and different orientation, and realize that in fact the iron selenide on monolayer have two things. One aspect is the charge transfer, which I have not touched about it. The other is the monolayer. In other words, if you look at charge transfer or doping of the system, you can get them to 40-50 range, but in the 60 range, you need additional the interface phonon contribution. So more recently, we did a more study. So the question will be where this doping coming from? And if you put iron selenide on substrate, then of course there's band bending and charge transfer, this phenomenon that's very typical. So what we want to do is to use the Langston tightening and Stromsen tightening as a platform. What they say is that if we grow start with Stromsen tightening and grow different thickness of Langston tightening, you have a different amount of carriers, charge reservoir to dope in your film. This way you can dope the same film, but maintain the interface quality to be consistent. So that's what we did. And just to say that we can grow LTO on STO in an epitaxial way, and we can also grow iron selenide on top of that, depending on with the thickness of LTO being adjustable. Okay. So here are some of the data. Okay. At the Fermi surface of those films. The lower part of the Fermi surface of the STO substrate, that's a 1 unit cell, 3 unit cell, 20 unit cell of LTO on top of that. Okay, and you can clearly see that as you grow the grow the LTO thickness, you can see the detail doesn't matter, but there are more and more electrons at the surface. That means there's more potential for charge transfer. On the other hand, if you put the iron selenide on top of that, you find that independent of the amount of carriers at the surface of the substrate, the Fermi surface of the iron selenium remain to be identical. So in other words, even though your substrate, you can see the electron density at the low thickness changes a lot, but the carrier density as measured by the Fermi surface, as well as the superconductivity as measured by the gap, seem to be completely robust in this system, almost as if there's a magic doping in the system. Here we compare our work with some of the earlier work of potassium and lithium intercalation. You can see that in the case of those intercalation work, they find the superconducting transition temperature are actually discrete, okay, either at this TC or this TC. And in this case, and they have both potassium and lithium in this case. Okay. Our work suggested doesn't matter how many carriers in the substrate, the doping in the systems appear to be completely anchored, and also superconductivity is it. So this also explained in the literature, there's so many groups working on the film and growth, they always ended up with the same doping, same TC in this system. So that is very intriguing. And we have some ideas, and this is telling us that we are far from understanding selenide. We have some ideas about the phase diagram, but I think my time is over. And let me just put this up to summarize. We try to say that the multimodal ultrafast technique, the terahertz blocking permits the precision measurement of coupled interaction are not possible otherwise. Suggest interaction in electron-electron interaction, enhanced electron-phonon interaction. The interface engineering also gain insight how the coupled interaction enhance superconductivity in the system. So let me now stop sharing and
thank you very much.
great, thank you. Yeah.
Thank you. Fantastic talk. I guess anyone have any questions? You can raise your hands. I guess while we're waiting, Zach, may I ask what are some of the potential mechanisms at which the doping is pinned?
Yeah, we have a speculation with the iron selenium system may have another insulating phase nearby, and the barrier to enter that is higher. Therefore, even though we have a lot of electrons at the interface ready to go in, but it couldn't overcome that barrier. And in a more disordered system like potassium or lithium sort of doping, then things are rounded off easier. That's probably the reason, because with the way doping through interface, it's a fairly clean. So I would say it's a more clean limit. But I think it's more of a puzzle than an answer yet. But that's how research goes. Yeah.
I see.
Hi.
Amalia, yeah, you wanna have a question?
Hi. Very good talk. So my question is more about the electron-phonon coupling, and if there is any other ways in which we can kind of establish some tests for it, like an isotope effect type of test, in which we can put all the experimental and data together to get it sorted, because we also speculated about the role of acoustic phonons that might affect criticality. So I just wonder, how do you see these phonons really manifest, and what type of phonons might be relevant?
We definitely know that strong correlation is very important in iron selenide system, but since you asked about isotope effect, in iron selenium iron-based superconductors, there's a very strong isotope effect in the system. With alpha is pretty value pretty big. It's about 0.4. Right? So in that system, On the interface work, that has been, there's isotope exchange of oxygen in that work, and shows that indeed the replica is a phenomenal type of a feature. I do not follow exactly what you mean by criticality. I guess there's a particular theory or particular idea you have on this subject. So.
No, I was wondering if there is a difference between acoustic and other type of phonons which you have in mind when you think about what influences your results.
Now I got it. Yeah. Now the phonons we are looking at here are all optical phonons. Okay. One is about 5.3 terahertz, and one is just very high frequency. It's almost 80 or 90 millimeter. That mainly had to do with our ability to see them. In the sense that those are the phonons which are very visible in the experiment we're doing. But what we wanted to do in the first set of experiment is to say that, can we benchmark in one case a experiment that we can get the critical quantities directly from experiment, so that we do not need an assumption. In that case, then you can say you can make a more direct comparison with the microscopic calculations.
Yeah. Thank you.
And then I think Elia, a question.
Yes, thank you very much, Dix, for a very nice talk. I have two related questions for the first part on the iron selenium. The first, when you said that there is this big difference between DMFT and DFT, if I try to boil it down, does it, I mean, in a simple terms, does it simply correspond to the fact that if you compare DFT and DMFT, the sizes of the pockets that you get in iron selenium are very different. So if I would just shrink the size of the pocket and would compute, within the effective series, the effective potential, it's just needed that I need to have a much smaller pocket to get the right number for the deformation potential. That's just a clarification question. And another question is that when you do the measurements in iron selenium, I understand that you do it starting from the nematic phase. So in principle, nematicity can affect also this strength of the deformation potential. So in this regard, I know that there were also measurements done for the 1 to 2. You also cited that. So do you know how large, is there any difference in the deformation potential if you compare it, let's say, nematic state and 1 to 2, where you don't have, for example, nematicity, or in any of the compound where you don't have any nematicity?
Okay. On your first question, it's probably a more detailed look at what it means in the calculation. You probably are right on that, and what will be the mechanism. One particular thing I like about the dynamic mean field theory, two things. One is it's a very different prediction on this quantity from the other calculation. And I also found that that theory is done before the experiment. B is that if you really look at the coupling modes, they predict one thing which is very non-trivial, the non-monotonic change. They kept, remember the pressure dependence of TC or the coupling is a non-monotonic. And that non-monoticity is non-trivial, and that appears to be captured in this calculation. As for your second question, okay, my take will be indeed you are in a particular experimental phase, and the nematicity is there. My take will be that probably doesn't matter as much. That'll be my guess. I can't prove it. Okay.
Okay, thanks. Thank you.
And Henri?
Yes, sorry, I arrived a little bit late. Zach, but
Great
I like
seeing you, Zhao.
I like the end of your talk. Just a simple question: Do you pretend that superconductivity is due to electron phonon behavior in that case?
In the monolayer system?
Yeah.
Or no, we in the monolayer system, our working assumption was there is a pairing mechanism of itself, and we actually do not necessarily know exactly what it is, but in our analysis we assume it's of electronic origin. Then we say if there's a superconductivity already, what will a small q phonon do to such a superconductivity? And the way the reason we know it's a small q is that I have a band structure and I see a shift. Remember, I said I have a loyal copy of the two. Okay, and if the phonon q is non-zero, then I have all momentum mixed up. I will not have this detail being copied. That dictates the q is small. As you know that small q can enhance superconductivity of electronic origin or phonon origin the same.
Okay. That could be a little bit similar to what we think in the case of cesium-360 in the full arrays,
Yes.
in which we have a high TC and near remote transition, and it could be that it is an enhancement due to the correlations.
Yes, I think we would just. I'm interested in the systems. They seem to have more than one thing going on, and I'm thinking that those are lucky cases. The more than one thing actually help each other. They don't often do. They usually go against each other, but occasionally they do help each other, and that's probably why. Yeah.
The last question by Qimiao.
Yeah, it's just a quick follow-up to what Ming asked. So experimentally, when you change a substrate, you said the Fermi surface doesn't seem to change.
Yeah.
Is there anything that changes, say, effective mass or the bulk FERC, for instance, there's some high energy features in interpreting terms of low Hubble band, anything in the spectrum?
Okay, there's a lot of change before we put on iron selenium. Okay, you can see Fermi surface is changed by a factor of 4. Okay, so as we prepare different substrates, but somehow once you put an iron selenium, it doesn't matter how many electrons are on your surface to be doped. They end up with the same. This still need to be more work to be done. And as you can see that the level of question you're asking, the Fermi surface, the Fermi velocity and all that, probably the error is too big to see any difference yet. But my guessing, now I'm guessing because it's a big error bar. I'm guessing it's not going to change much because the superconducting gap doesn't change much.
Very interesting. Thank you.
I guess, if I may, as a follow-up question, yes, I'm imagining the strain on the iron selenium is also changing by the different substrate. Is that true?
No, the tuning, what you're referring to Heike's work, those are crystals, not a substrate. The strain tuning. That's what you're.
I'm in the epitaxial strain for the last part. The different substrates, they may force the monolayer to have it.
No, that's the earlier work. Strong titan has many things special, right? Lattice constant, dielectric constant, a lot of things. So we did the work on different surfaces, 100, 111, 110. They all look the same. And also there's a titanium oxide. They all look the same. So then it boiled down to a question whether the chemistry of there are two possibilities. One is the strain doesn't matter, will be one answer. The other is the chemistry of the system is such that it always, like in the end, it forms some sort of magic interface. Okay, in that case, you may start out with something you think is very different, and your naive expectation, you will say you end up with something very different. But in fact, when the film is grown after the cooking, the annealing and all that, you end up with the same thing. That's also possible. That will be another magic type of thing. And this is still, I think this is very rich, but it's still working in progress.
Thank you very much. Thank you, Zex, for your time. Thank you very much. I guess we'll move on to the second part. Thank you, Igor, for your patience as well. If you may start sharing your screen.
All right. So let me start the presentation mode. So is it in the presentation mode currently? Oh, no, it is.
There it is.
Right.
Thank you very much, Igor. So you can go ahead. Thank you very much. Yeah.
Okay, so I want to start also thanking the organizers for giving me an opportunity to present our recent work on magnetic superconducting topological surface states on iron chalcogenide family, and for organizing this very nice series. So this work is a work of our Brookhaven neutron scattering group that was the first. The lead author is Yang Mu Lee, who did the most of the hard work in this project, bringing it to fruition. So it started as a neutron scattering project where we did neutron scattering studies in collaboration with different members of our neutron scattering group on top, and with an excellent support of a high-spec instrument team at Oak Ridge National Lab. Here on the bottom left, and then as on samples that were made in our neutron scattering group by Genda, Chedamir, and Jijunju. And as our work progressed, we realized that we need to comprehensively microscopically characterize our samples or small pieces of our neutron samples, and that was done at Brookhaven Center for Functional Nanomaterials in terms of chemical and resistance microcharacterizations in collaboration with Fernando Camino, and then the very comprehensive characterization using the micro-resolved RPES measurements in collaboration with Peter Johnson's group, in particular Nader Zakia performed a lot of measurements which were analyzed and systematized by Yang Mu to obtain the results that I'm going to report to you here. All right, so the outline is such that I have a rather extensive introduction, which I hope to skip rather fast because it emphasizes the points that were raised by different speakers in the series, and in particular, the importance of strong electronic correlations that was emphasized by the previous speaker to set up the main problem that we have addressed in this work, which is the puzzle of inhomogeneous superconductivity and topological properties that have been observed in the iron chalcogenides recently by STM studies, and our resolution of that puzzle in the form of iron and tellurium composition controlled phase diagram of different magnetic superconducting and topological phases that we have discovered in this material series. All right, so iron chalcogenides, as everybody knows, are the simplest family of iron-based superconductors with layered structure. Here is another rendering of the structure from a DFT work, which sort of illustrates formation of bands via hybridization of iron 3D and tellurium 5p orbitals. And the band structure computed by DFT at a very early date, so in iron telluride, was very similar to the one in iron pnictide materials, with a hole pocket at gamma point near Q equals 0 and an electron pocket at M point pi pi. And so here is a illustration of a brilliant zone with two pockets, and then there is a nesting between gamma and M points, which in the itinerant electron picture suggests a tendency to magnetic ordering at a wave vector pi pi. I know that there is nothing at x point pi 0, and nevertheless the parent state of iron chalcogenide superconductor family, iron telluride, has magnetic ordering which occurs at exactly X point, which this is so-called double stripe ordering, which is difficult to explain in the simplistic itinerant electron picture based on the DFT calculation. On the other hand, the parent phases of pnictide superconductors do show the single stripe, so-called magnetism with propagation vector pi pi corresponding to this endpoint, and that can be rationalized by nesting. Of course, when materials are doped towards superconductivity, the long-range order goes away, and in the doped compositions which are superconducting, the dynamical magnetism is persists in the form of dynamical fluctuating short-range correlated patterns, which nevertheless preserve the features of the electronic state observed in apparent phase. For example, the short-range version of the this single stripe order, whose real space version is illustrated on the bottom right, is that would be measured by neutron scattering, is shown in the right middle panel with strong intensity at pi pi points here, while neutron scattering would show a pattern with stronger intensity at pi 0 points in a short-range dynamical version of double stripe magnetic order. All right, so the resolution of a puzzle of double stripe magnetism can be looked into in the strong correlations characteristic of these iron telluride or iron chalcogenide family. So these are very early calculations by DMFT, which by Gabby Kotler's group, which show that indeed iron telluride is the most strongly correlated among all iron-based superconductors family, which leads to substantial renormalization of bandwidth or effective mass. But more importantly, it leads to a substantial decoherence, which can develop upon rising temperature to reasonably low values. For example, in iron telluride, DMFT predicted that a coherent band structure near the Fermi energy exists at low temperatures and gets substantially decohered at reasonably low temperatures of the order of 100 Kelvin and above. That was actually consistent with our earlier neutron scattering work, where we have observed a change in the total magnetic scattering that can be assigned to local moment fluctuations, from local moments corresponding to spin 1 or 2 localized electrons at low temperatures to local moments of spin 3/2 or 3 localized electrons at high temperatures. So this is in agreement with 1 electron that gets coherent upon cooling, leaves its local moment localized state and goes into a conduction band. And this was consistent with the measured resistivity, which became more metallic, corresponding to appearance of conduction electrons, and decrease of magnetic susceptibility, illustrating decrease of magnetism, of local moment magnetism. We have later discovered that this transition is actually accompanied by formation of the bond order wave made of zigzag ferromagnetic chains. So this is a sort of orbital order that develops when electrons become coherent. This order, by the way, explains this double stripe magnetic order as the order of antiferromagnetically coupled ferromagnetic zigzag chains, similar to the situation in manganites. But the point I'm making is that the development of electronic coherence and cooling leads the way to development of electronic instabilities, such as formation of orbital order or of a superconductivity. So one needs electronic coherence in the first place to form superconducting state. Now, later studies by ARPAS, by the group of the previous speaker and Mingi in particular, have provided direct evidence of orbital selective band decoherence and strong renormalization effect in iron telluride selenide materials. So the bandwidths measured by ARPAS were much narrower than the bandwidths obtained in typical DFT calculations. calculations. In fact, the renormalization was orbital dependent and reached as much as order of magnitude for DXY bands. And it was also shown directly by Mengiz that the coherence of DXY band goes away upon warming in qualitative agreement with the predictions of DMFT and with our observations of localization of one of the electrons. So the effects of strong correlations are extremely important and lead to decoherence of electronic band structure near the Fermi level in this material family. One way to sort of phenomenologically take into account these effects of electronic strong correlation in a DFT approach would be to make DFT calculations in a magnetically ordered state. And it was shown by Peter Johnson's group that one can, in principle, sort of rationalize the measured, RPES measured band structure near the Fermi level with, these are two bands near the Fermi level, alpha 1 and alpha 2 measured in iron tellurium 0.45, selenium 0.55 composition. So one can sort of get a good agreement between this band structure and the magnetic, the calculations of DFT calculations in the presence of magnetic order. But what they discovered is that it is also extremely important to take into account the spin-orbit coupling, which is strong on tellurium atom and is transferred onto principally DXZ, DYZ derived bands, alpha 1 and alpha 2, which are spin orbit split. So this is actually this was actually interpreted as very large spin orbit splitting of these two bands at the Fermi level. So I think this was one of the earliest demonstrations by RPES that spin orbit coupling is extremely important in these materials. It was also shown that this alpha 1 band, this is a bulk band that we will be I will be talking about later in more details, is actually non-dispersive in the direction perpendicular to the AB plane, which actually also contradicts the simplistic DFT calculation, but that is just another failure of DFT. Oh, anyway, despite all these failures of DFT, several groups in around 2015, around the same time, came up with a DFT-based prediction that there is a band inversion in this iron tellurium selenide system for certain selenium-tellurium composition, near half, and there is a formation of a topological surface state related to this band inversion. Of course, some of the authors, in fact, were cognizant of the fact that correlations can significantly modify or negate this picture. In fact, in one of the papers, there was a DFT, DMFT calculation in an appendix showing that a decoherence of the bands develops. But nevertheless, the experimental verification, I mean, there were experiments conducted following these predictions, which indeed observed formation of this topological surface state. And it was in quantitative disagreement with the theory because theory predicted it to be way above the Fermi level. But luckily, in experiment, it was observed right near the Fermi level. So it was a disagreement which was very favorable for us. Now, in the presence of, and that this is a topological surface state, of course, relies on the fact that there is a band inversion, and there were subsequent studies, and one of these studies was actually reported earlier in this nice seminar series by Kanigel. So Kanigel's group has indeed shown that this alpha 1 band does experience band inversion. It changes symmetry along gamma Z line, and that was shown by measuring intensity along gamma Z, and showing that that intensity varies. So anyway, there is a band inversion. There is also another study that showed directly band inversion in a series of monolayer films of iron tellurium selenide with different doping. So there is band inversion. In the presence of the superconductivity, and the superconductivity in the RPES shows up as this superconducting condensate peak split off the Fermi surface of the Fermi level by a superconducting gap. This is this bright flat feature here. So this is a measurement on the same series of materials also by Kanigel's group. And I'm showing here, showing this measurement here is because we will use this feature to quantify the presence of superconductivity in our sample, in our work. So in the presence of superconductivity, which can be quantified by the presence of the superconducting condensate peak, the other thing I want to mention, looking forward, is that you see that the superconducting condensate peak is extremely sensitive to the iron content. In fact, in this work, they mentioned that this change of the superconducting condensate peak occurs on decreasing iron content, but the change in Y, this iron content, was so small that they weren't even able to report numbers. So they just said it's bigger here and smaller there, but it was, I think, within 1%. Okay, so nevertheless, in the presence of this bulk superconductivity that can be evidenced by the superconducting condensate peak in RPAS, the surface superconductivity can be induced, and in that surface superconducting state, topological superconductivity would host Majorana zero modes in the cores of the vortices on the surface of the superconductor. And those vortices and the presence of those Majorana bound states in the cores of topological vortices can be measured by using STM, and they show up as zero bias peaks, which were found experimentally and reported right following the report of the surface state itself. And so it would be a total end of the story, except that follow-up work reported that along with the topological vortices that hold the zero bias peak here, as a function, so this is intensity as a function of bias and the position in the vortex core. So you see this is a zero bias peak. There are also nearby vortices which do not show Majorana zero mode, and so there are trivial vortices corresponding to a regular non-topological superconductor. Now, another work actually mapped the distribution of trivial vortices, which are shown by white diamonds here on the and topological vortices with Majorana bound states, which are shown by red circles here on the surface of superconductor. So what was observed is that this topological surface superconductivity seemed to be strongly inhomogeneous. So it presented really a puzzle. Now, approximately at the same time, there a report appeared showing that, again, by Josephson STM measurement of this iron tellurium selenide material with tellurium selenium composition of 0.55, 0.45. So the report appeared that showing that the superconductivity itself is strongly inhomogeneous in this material. So the panel B here shows distribution of the superfluid density, while below panel E is the inhomogeneous distribution of the superconducting gap measured by Josephson STM on the surface of this material. And in fact, the inhomogeneous superfluid density is also accompanied by inhomogeneous normal state resistance on the surface. So the superconducting properties of this material and the electronic properties seem to be substantially inhomogeneous as measured by STM. In fact, I want to mention that earlier, very similar, in my view, the electronic inhomogeneity of the superconducting state was observed in viscous cuprate superconductor by the same Josephson STM. So this panel C shows the variation of the superconducting gap as measured by Josephson STM on the surface of viscous sample. In that case, it was explained by virtue of the proximity of that material to the electronic nematic transition, which can be understood as a quasi-two-dimensional, which can be described by quasi-two-dimensional random field Ising model, which shows a large critical range where two different phases coexist, and theoretical simulation of this observed inhomogeneous electronic state found that it is consistent with the random distribution of these Ising domains, which result from the proximity of the material to the phase transition line. Okay, but in the iron tellurium selenide near 0.5 doping, it would look that the material is far from the transition line between the parent state, where magnetism is double striped with neutron magnetic scattering looking like this, to a magnetism typical of a superconducting phase, which shows a single stripe type magnetism, which peaks at near M point. And so the question is, why would the superconductivity and topological superconductivity be inhomogeneous? An answer, or a possible answer to that, lies in a well-known sensitivity of this family of materials to iron composition. So it has been known for a while, if we look on the panel on the left, this is from Vienna et al., that in the iron, in order to have a well-developed bulk superconductivity at compositions between 0.3 and 0.5 selenium doping, you need an iron deficient materials in nearly nominal iron, for nearly nominal iron content, even for selenium doping of 0.45, material can be non-superconducting. So iron represents a substantial handle on the appearance or disappearance of superconductivity in the material. However, there are many ways of destroying superconductivity. You can have magnetic scattering of some interstitial irons. You can have a disorder, potential scattering, or there can be a possibility that, in fact, iron tunes transition between two competing electronic phases. And while, in fact, it looks exotic, it is exactly the possibility that I will try to convince you is the case here. All right, so in order to understand what's happening, we took two big samples with slightly different iron composition and measured magnetic neutron scattering on those. So these are shown on two right panels here. So the middle panel shows magnetic neutron scattering pattern measured on sample A, which was prepared by Gendago and our group, with having slightly more iron than well superconducting sample B. So we checked that sample A is non-superconducting not only by measuring, and sample B is superconducting, not only by measuring a magnetic susceptibility on a small sample, but these measurements were performed using polarized neutron scattering, which has unique sensitivity to the appearance of superconductivity in the bulk sample. If sample becomes superconducting and undergoes a transition in a small magnetic field, which we use to guide neutrons polarization, the neutron beam becomes depolarized. So from that, we actually know that a big piece that we measured of type A, this one, is non-superconducting, causes no depolarization of neutron beam, while this big chunk is superconducting. And so in this measurement, we have what we have observed, that a non-superconducting sample demonstrate magnetic scattering pattern dramatically different from a superconducting sample. This one is typical of a single stripe, of a double stripe magnetic correlations, while the superconducting material, sample B, shows a pattern typical of single stripe magnetic correlations. And the non-superconducting sample A showed a pattern that was very similar to the one that we measured previously in weakly sulfur-doped, sulfur-substituted material. So what that shows is that apparently there are just two different phases electronically, the one from which superconductivity can appear and the one from which superconductivity cannot appear. All right, and in order to confirm that, we have measured the non-superconducting sample at high temperature, 300 Kelvin, and the scattering is essentially the same. And we measured the superconducting sample at a temperature above the superconducting transition, and the scattering pattern is also the same as below. So what this tells us is that we observe change between the two samples, A and B, non-superconducting A and superconducting B, which is characteristic of a parent non-superconducting state. So that something happens to a parent electronic state that dramatically changes the local magnetic correlations with slightly changing amount of iron. So we were, next question was, is it really a small change in the amount of iron? So we need to quantify the real composition of our materials and to measure their electronic properties. And so we did that by choosing a number of representative small pieces from each of the two samples, 9 in total, 5 from one, 4 from another. Each little crystal was subjected to thorough analysis of its elemental composition and electronic properties by making a 100 by 100 micron grid on the surface of that crystal, and then measuring the composition, the elemental composition in each cell of that grid using EDS, measuring the electrical resistance on that little element of the grid by using the microprobe at nanocenter, and by measuring the local electronic ARPAS spectrum by using the micron resolved ARPAS. And so we observed that there are 3 types of regions, just 3 types of spots on which different ARPAS spectra are observed. We either observe an ARPAS spectra, such as in this violet region, which contains bulk band, a surface state, this bright yellow spot, and a superconducting condensate peak. There are other regions, like one marked by green spot here, where the bulk band is observed and the superconducting condensate peak is observed, but no topological surface state is observed. And yet there are other regions, like the one that's shown here by yellow, where a totally incoherent band structure is observed. In other words, no coherent features can be easily identified. In fact, I understand that in many previous studies, in many previous ARPAS studies, when such spectrum would be seen, it would often be dismissed as a bad spot. Now, we have measured all spots on the samples, and so if 30% of your spots are bad spots, and you can correlate the behavior of the spectra in those bad spots with their chemical composition and their resistivity, that would tell you something, and that's exactly what we did. So it turned out that these type of bad spots typically have higher room temperature resistivity. Also, upon cooling, they show non-superconducting behavior. And while the other 2 spots have lower resistivity, the ones that have coherent features in the ARPAS spectrum, lower resistivity, as well as they show the superconducting transition on cooling. So the first question, of course, the main question we asked based on the neutron scattering results was what is the composition of our samples? And so what we did, so what this represents is a histogram of composition measured on these humongous compositional distribution measured on these humongous grids on 9 samples. And what we see is that indeed the main difference between sample A, which is a non-superconducting, and sample B, which is superconductor, is that sample B has really slightly deficient average iron content, while sample A is nearly stoichiometric, but probably maybe 0.5% more iron than stoichiometrically allowed. And then the iron and tellurium compositions are very similar, near the nominal 0.55, 0.45 proportion. And so if we plot the probability of encountering a certain composition in a sample as a function of iron on the x-axis and tellurium on the y-axis, then sample A, non-superconducting one lies here, and sample B, the superconducting one, lies here. And I will show what this line is. This is a line of a transition as we have determined between the superconducting phase and the non-superconducting phase. Now, how do we determine this line? We determine this line by analyzing the ARPAS spectra that were measured. So each spectrum was modeled by fitting to a spectrum containing 3 features: the bulk band feature, the topological surface state feature, and the superconducting condensate feature. So the intensities of these 3 features were fitted for each spectrum, and the typical, so this is a color plot of the typical fit at 5 Kelvin. This is a color plot of the typical fit at 19 Kelvin above the superconducting transition temperature. This is just to show that there is a gap in a topological surface state that opens upon entering the superconducting state. This is something that was recently reported by Peter Johnson's group in this paper here. The main point I wanted to emphasize here is that our model gives a very accurate account of all the features that are observed in the spectrum. And so we used it to quantify the presence of a certain feature, quantifying the existence of a certain electronic state under that spot on a sample. And so here what we do, we represent the intensity of each of the features as a function of iron content and tellurium content. So this makes us this forms a sort of a phase diagram. So panel A shows the intensity of the superconducting condensate feature, and we see that iron deficient spots have stronger intensity or strong intensity of superconducting condensate feature, while it fades in the region of phase diagram, which is iron rich. Similarly, the coherent bulk band, its intensity is strong in the iron deficient region, and then it fades in the region where iron content is higher. And so these are sort of those bad spots where we don't see basically, among these are those bad spots where we don't see basically bulk band. Now, in the same phase diagram, we can represent the resistance that we have measured using the microprobe. And what we see is that iron deficient region has more conductive surface than the iron rich region. And it correlates perfectly with the intensity of the bulk band and the intensity of the superconducting condensate peak. So based on these three measurements, we have refined, based on the 50% threshold in the corresponding variation of the corresponding property, we have refined this phase boundary between the resistive, incoherent, non-superconducting state at higher iron content and the conductive, coherent electronically state that develops superconductivity. Now, it is only in the superconducting phase, but only at a high tellurium content, that the topological surface state feature is observed. So you see, this is the intensity of the topological surface state feature. We see that there is a separate region in the superconducting part of the phase diagram, which also hosts topological superconductivity. The Dirac gap that opens in this phase actually closes at the boundary of the and the phase boundaries. So the topological superconductivity arises together with the Dirac gap. We can make maps of various quantities that we have measured. In particular, this is a map of the different phases on that we have observed on the surface of this of a particular sample. So you see the dark violet, the dark blue or dark violet are spots where topological surface state and superconductivity are measured. The greenish ones are superconductivity that is a trivial superconductivity, and yellow are the non-superconducting spots with incoherent electronic bands. So to conclude, we have been able to construct a phase diagram which shows that at a higher iron content, an electronic state realizes, which is where the band structure near Fermi level is incoherent. It is characterized by a double stripe type magnetic correlations, which are most likely arising from strong correlation effects. And upon lowering temperature, no superconductivity develops, and correspondingly no topological surface state. At a lower iron content, we have a transition into a phase that does have coherent bulk band, which does develop coherent superconducting peak below below superconducting transition temperature, and at higher tellurium concentrations, this phase also hosts the topological surface state. So iron stoichiometry controls magnetism, coherence, electronic coherence, and electronic transport, and as electronic coherence develops, the superconductivity develops upon lowering temperature in a way similar to how the orbital ordering develops in iron telluride upon developing of electronic coherence. And the tellurium concentration drives the topological surface state, and when the increase of the spin orbit coupling of tellurium gives rise to the topological surface state. Now, the puzzle of the puzzle that we were the puzzle of inhomogeneous superconducting and topological states is basically answered by the position of these samples. And I need to mention something I forgot to mention, that samples used in most of those studies that have been reporting the topological surface state and Majorana modes, many of those samples, if not most, came from the same source, that we used in our study. So they were made by Gendagu. And so the superconducting samples, they were all representative of this B sample. And what we see is that it's right at the boundary of the phase transition line between a trivial and a topological state. Both samples are also close to the transition line between the non-superconducting and superconducting state. And so, in fact, even if samples would have been ideally stoichiometric, because that stoichiometry puts them in the proximity of phase transition lines, the fluctuations of electronic fluctuations that are intrinsic to those phase transition lines would be unavoidable. So the key to harnessing these topological surface state and superconductivity would be to try making a sample down here in the region of phase diagram, which is farther away from the phase transition lines. All right, thank you very much for your attention.
Thank you very much, Igor. It's a very beautiful experiment. I'm going to take advantage of my position to ask you first question, if that's okay. So for the slide where you show that for where you measure the low energy magnetic excitations for the three different, so the yes, this one.
Mm-hmm.
If you were to measure the rightmost sample with a fewer iron, excess iron at high temperature, what would you see? Would you see the same pattern? Or?
Very good question. Yes, it does develop incoherence, and the pattern changes dramatically in this direction.
Okay, great. That would be exactly consistent with our.
Yes,
on the same.
I have that measurement. It's just not. I'm working. We are working on it. Yes.
Okay, thank you.
You're absolutely right.
The second question is, if I can ask, so you only show the band dispersions around the gamma point. Do you also have information around the endpoint for this?
The ARPAS. This is a laser ARPAS that we have here in the building. So it only has a very small. In fact, we were beaten by the referee who were saying, you don't have an access to this other band that goes, at larger Q, and we were. I mean, the access to that band in a way is provided by us seeing the superconducting peak, which actually sort of comes from that band.
Okay, I see. Thank you very much.
Mm-hmm.
I think it was Pengcheng first.
Yeah. So yeah, very nice talk. Yeah, so do you know what happened to the excess iron? I mean, do you know the positions of these?
Sorry.
I mean, for the non-superconducting samples, right? I mean, you have a completely different magnetic spectra, right? How much more excess iron you have?
Pengcheng, yes. So you see, the thing that I do really find absolutely stunning is that, firstly, there is so little. So this is a histogram of iron distribution, right? So the superconducting sample, it's slightly less homogeneous, as you can see, but the average average iron composition is probably 0.98, right? So first of all, it's iron deficient. Of course, we are not 100% sure that it's 0.98. It might be 1.01. I mean, not 1. Maybe 1. The absolute accuracy of our measurement, its EDS, is not so great. The relative accuracy is very good. So what we can tell you for sure is that the composition of this one is just 3% different from the composition of this one. Now, to that accuracy, determining from a diffraction experiment either vacancies or interstitials, on the level of 1% is, I don't think it is feasible. So we don't know. The answer is there is so little difference in iron that we don't really know where it is.
I see. Do you have diffuse? Do you have a neutron diffuse scattering measurement? I mean, to show that maybe on Corelli or something?
I mean, we have. There is main. Okay, so. as I've just said, the amount of extra iron is so small that, of course, I have the measurement of. I mean, we have these. We have measured the full, volume with unpolarized as well as polarized neutrons. So diffuse scattering is totally dominated by magnetic scattering. So there is no structural diffuse scattering that can be seen to be associated with structural, disorder and imperfections.
Okay, thank you.
I think it was Christoph next.
Yeah, very nice talk. I was wondering, what is the difference in annealing, or how did you prepare samples A and B? Was it tellurium vapor?
Sorry, well, I didn't.
How did you prepare the difference between A and B, sample A and B? Is it different annealing times?
This was really sort of low tech, just putting in a little bit, varying the input composition of the input material, iron and tellurium and selenium.
I mean, usually these samples, they have excess iron, right?
Well,
you have to anneal them to get rid of the excess iron.
No. Okay, so no. So the sample B which is well superconducting and turned out to be slightly iron deficient according to our measurements, was just as made. So it's just again the optimized initial composition of. I mean, they did some research to optimize the compositions such that a well superconducting samples can be grown. So we did not do any post-processing to this sample.
Okay, and the second question is, what are the TCs, and did you measure heat capacity of these samples?
We did not measure heat capacity. No, we did measure, so on the small pieces of these samples, we measured the magnetic susceptibility and all the other measurements that I have just reported. The big samples were measured by neutron scattering. And as I mentioned, I mean, this was actually, I was always have this question, when you measure a neutron scattering sample and you say, this is a superconducting sample and this is non-superconducting sample, but how do you know? Now I'm telling you, I know for 100%, this is a superconducting and this is non-superconducting.
Heat capacity would be another method, huh?
Yes. Oh, you know what? I can show you something. I think I have. Oops. I have. Oh, here it is. So this is a neutron scattering measurement of a magnetic field, sort of a magnetic field trapped in a sample upon cooling. So this is a flipping ratio that measures how how neutron beam is depolarized as a function of temperature of the sample. And you see this beam is well polarized here above 14 Kelvin, and then boom, it goes down.
So DC is 14 Kelvin.
Right. Yeah. That basically is a measurement of a transition temperature on a bulk sample by neutron scattering. Very expensive measurement, but it was not the goal of the experiment.
Okay.
But it doesn't tell you the volume fraction, though.
Well, this is a difficult question. I truly cannot, but I can estimate. And I did an estimate, and it turned out I mean, 90% plus minus 20. Let's say it this way.
Okay.
Okay. Thanks. Yeah.
Sorry. So I guess Jamil.
Yeah. So Igor, I have a quick comment about something that you said on the site, which was about 100% FETE.
Mm-hmm.
You seem to suggest that around 60 Kelvin or something like that,
mm-hmm.
that the XY states develop coherence. So my comment is that I don't think that's right. I think all the indications are like the XY states stay incoherent all the time.
I did not say that it's specifically XY state.
But what I thought that's what you were suggesting.
No. Sorry, I said two different things. I said that in parent material, we have seen the development of we have seen the change in local moment here, mm-hmm. Which corresponds to, which can be understood as development of the band of the coherence in the band structure near Fermi level, which which bands or which orbitals are involved, we have no access by use from these measurements. Now, the other thing I said, it's I think I referred properly. Mingi should correct me if I was wrong. That was describing her measurement on iron, tellurium, selenium. I think near half dope material.
Specifically focused on FET.
Right. Right. So there, I think they showed that it is a DXY band that loses coherence.
Well, I don't think there's any establishment of coherence at low temperatures, but we can discuss later. It was a comment.
I thought that that's something that ARPA's data have shown directly.
FETE, it's fully localized.
No, not in FETE, in FETE.5 SE.5.
No, I'm focused on FET. My comment was about FETE.
Right. So on FETE, I mean, this is a picture that shows that there is an electronic coherence that is being established, but what bands are involved, we do not really, I cannot really say.
All the orbitals have been looked at, and there's no evidence for any of the orbitals becoming coherent at that temperature.
Well, maybe there are some other explanations, but it's clear that the amount of magnetic scattering and the resistivity and the susceptibility are all correlated, and it's all correlated with the development of this.
Very interesting neutron measurement. I'm just, well, the comment was very specific about electronic.
Yeah, so my way of rationalizing it is by comparing with the Gabi-Kotlar's calculations, which show that electronic coherence is developing here. But if you say that there are other ways, I mean, I'm open.
The comment is that experimentally, there's no indication of establishing coherence in any of the orbitals at that temperature.
At low temperature. No, coherence is established at low temperature.
At any temperature.
So experimentally, there is a change of resistivity behavior from bad metal where resistivity increases with lowering temperature to a good metal where resistivity decreases with lowering temperature.
I don't have a comment on that. I'm just saying that from single electron excitation spectrum, there's no establishment of coherence.
Well, maybe there are alternative explanations of this. I don't know. I mean, that was our way of rationalizing this observation, experimental.
Henri, do you have another question? Or?
Yeah, well, I have a simple one. I like the neutron scattering data, but I wonder when you are comparing to ARPA's data, is it safe to compare bulk measurements to surface measurements? In some sense, how do you know that the surface would have similar compositions, etc.? This seems a little bit dangerous for me.
Okay, the question is, in our view, the question is twofold. One, and that is something that Peter Johnson sort of taught me to say, and I truly believe that this is true. RPAS is a technique that is sensitive to both surface features and bulk features. So
not the bulk of the sample. No, it's not the bulk of the sample. It's still right on the.
No. You see, what that says is that if there is a bulk band in the sample, you can also measure it on the surface.
Of course.
Yes, so that is one. The other is how representative is this measurement of a particular surface of this particular sample of a bulk. Now, if we take, in this case, we measured 2,000 spots. So we basically take 2,000 different surfaces from the bulk.
Mm-hmm.
And we see a clear correlation between our measurements. In that way, we believe that just statistically, these are representative of the bulk.
It's statistical, but you are not measuring the same spot with neutron scattering and ARPAS.
No, but I'm measuring the average of all the spots measured by ARPAS with neutron scattering.
You're comparing the histograms of both. Okay.
Right, yes, exactly. But we only have three, but you see, we are aided by the fact that we only have 3 types of ARPAS patterns. and they can be correlated to two types and only two types of neutron scattering measurements.
Well, one has to look in detail to try to see how these correlations are really. But okay, I accept what you say.
Any other questions?
Thank you very much.
If not, I suppose we can close the session today. Thank you both, Igor and Ziax, at the lead earlier. Thank you both very much for your time.
Yeah, very, very nice time.
Yeah. And
thank
I guess
you. Bye-bye.
Thank you, Igor. Yeah. Thank you, Ziax.
Thank you.
Thank you all.
Bye-bye.
Yeah, good to see everybody.
Hello. Bye-bye.
Good to see everybody. Oh.